First question, where or what segment does the cart move the greatest distance? So that's talking about for a velocity versus time graph, that is area under the curve. So I'm going to break it down from A to B, B to C, and D to E. Area is just going from the curve to the x-axis. So that's my first area, that's my second, third, fourth. Now you don't have to actually calculate it. It should be pretty obvious that A to B is the greatest area. Which of the following is true about the motion? The cart is at rest from B to C. From B to C, it has a velocity of 8. That is not at rest. You would need a velocity of 0, so not true. The average acceleration from A to B is less than the average acceleration from C to D. Average acceleration would be the average slope. So this is 8 over 2, which is 4. And from C to D is 8 over, oh sorry, this is 8 over 3. Just kidding. 8 over 3, which is not 4, and then this one is 4. 8 over 3 is less, so that is true. The cart is slowing down from D to E. D to E is actually getting faster, so not true. And position at C is the same as position at E. So here and here would only be the same if these two areas canceled out. It looks like they might, but we have to actually calculate. This one has an area of, oh God, I don't know, whatever 2 here is, and 8 divided by 2, so that's just 8. And then this is 1, 2, 3 times 2 divided by 2, so this is 6. 4 divided by 2, this is 6. So 8 and negative 6 do not cancel out, so they are not at the same position. This one is going to end a little ahead of where it was at C. All right, another velocity versus time graph ranking displacement, so areas. So C is definitely the least amount. Now between A and B, if we look, this is a triangle with 2 times 2 divided by 2, which is 2. This is 2 times 1, which is also 2. So A and B actually have equal areas. So A equals B, and both of them are more than C, and all of them are greater than 0 because they're all positive areas. None of them are negative, like below the x-axis. Your answer is C. For section B, friction A versus compared to friction, not friction A, force A compared to friction force. We know that this had a force of FA1, and B had both FA1, because it was the entire time, and friction force. So if we're looking at this and we're saying, okay, B is at a constant velocity. Constant velocity means balanced forces. So if your forces are balanced here, that means the applied force must be equal to the friction force. Because otherwise, if FA1 was bigger, it would continue speeding up. If friction was greater, it would slow down. Not what happens. It's constant velocity, so it's balanced. How does the applied force in section C compare to the applied force the entire time? So section C, I still have FA1 because it said I have it the entire time, but you also have FA2. So I'm going to draw a like free body diagram for each situation. A has force A1, B has both of them balanced out, and then C has still FA1 because they all have the same FA1, but now it has another force FA2. A had a positive acceleration like this. This one had no acceleration, which is why they're balanced. And C was slowing down, which means it has an acceleration in the opposite direction. That means that second force, the FA2, must be in the opposite direction, so something like this. Now the reason that I drew it bigger is because I know it's accelerating this way, so not only is it this direction, but it's greater this direction because it accelerates this way and wins. So I definitely know that FA2 is greater than FA1. So FA2 is greater, we can cross off these two. What this one is saying is FA2 is somewhere between greater and 2 times greater, and this is saying it's more than twice as great. So here you have to actually look at the accelerations. So if you look at A compared to C, C has a greater acceleration than A did. So if you compare this net force to this one is not just enough to balance out A and then a little bit, it's enough to balance out A and then be even more acceleration than this one was. So it's more than double this one. So D. The object's changing kinetic energy in section A. So my initial velocity was 0, my final velocity is 2. So V0 is 0, V final is 2, mass is 4. So I'm going to do 1/2 mv squared. my initial velocity, or sorry, my initial kinetic energy was just 0, so I'm going to find my final kinetic energy. That's going to be, is this 8? Yeah, it's going to be 8 joules. So if I have 8 joules and I started with 0, then the change in kinetic energy is 8 joules. Phi is at a constant velocity, so your change in kinetic energy is actually nothing. What if there was not friction? So if I did not have the friction force, then A would have continued on like this, right? So the change in kinetic energy would have been, I would have had an initial velocity of 2, so V naught would have been 2. If I accelerated for 1 more second, well, the acceleration was 1, so this just would have been at 3. Your final velocity would have been 3, and you would have had a change of 1/2 mv squared minus 1/2 mv squared, final minus initial. Mass of 4, final velocity is 3 squared, minus initial velocity of 2 squared. So this would give me 18 minus 8, so that would be a change of 10 joules. Alright, we have a constant acceleration of positive 2, and we have an initial velocity of 8 in the negative direction. Most easiest, I think, is to start with your velocity versus time graph. I start with negative 8, and then if I'm going up to positive 2, this would cross the x-axis at 4. So if I'm looking at t equals 3, that's in here, that is a negative velocity, and it's a positive acceleration. So this is getting slower, negative velocity getting slower, that's moving in the negative direction, getting slower. Negative velocity, this right here is just the sign of the velocity. Whether it's speeding up or slowing down is if B and A are the same sign, that's speeding. And if they're opposite, A and B are opposite, that means it's slowing. So here, this was a negative velocity, so negative direction, and opposite, A and B are opposite signs, so getting slower. At t greater than 4, so that's something like here, now I have a positive velocity, so that means I'm moving in the positive direction, and I have a positive acceleration, same time getting faster. Also look at the graph here, like that's definitely getting faster, so speeding up F. Ball A is dropped from rest at the same instant ball B is shot horizontally from the same height. Which one takes the longest time to reach the ground? Think about the amount of time that it takes to reach the ground just depends on the y part, right? What's pulling it down is the acceleration due to gravity. They both experience the same acceleration due to gravity. They both start with the same initial y velocity, right? They both have no y velocity. This one just happens to have an x velocity. But x and y are separate, so going something faster in the horizontal direction actually doesn't make it come down any faster at all. So their time should be the same because everything in the y component is the same. They have the same initial y, they have the same acceleration, they're following the same y distance, so time should be the same. Now the speed when they hit the ground is not the same. This one has an initial speed of 0, this one has 0 y velocity, but it does have x, so when these hit the ground, they hit with the same y velocity because they've accelerated the same amount for the same amount of time, but this one also has an x velocity. So definitely ball B would be the greater one because it also has a Vx, right? Same Vy with more x velocity. You also can think about it as A started with potential only, B started with the same amount of potential and kinetic energy, so when they hit the ground, right, they both have just kinetic energy. This guy's going to have more because it started with more total energy. More because more total at the start. Right, a ball is thrown up in the air but at an angle, so like this, and I'm looking at the highest point and saying which is true. It's in equilibrium. No. If it was in equilibrium, the forces would be balanced, it would be at rest or at a constant velocity, not what's happening here. It has 0 acceleration. No, it has an acceleration of negative 9.8. Gravity didn't turn off because it's at the top. It has maximum kinetic energy. False. It has minimum kinetic energy. It has maximum right before it starts deaccelerating or after it's accelerated back down here. It has maximum potential, but that's not what it said. There are no forces acting on it. False. There's gravity acting on it. There is no velocity. This is the one that most people pick. It's actually not true. I have no y velocity, but I still have an x velocity. Your x velocity is constant, right? There's nothing slowing it down in the x direction. So that means it can't just turn off here and then continue moving sideways, come back, right? Your x velocity is staying the same the whole time. So E was not true. It has an x velocity. It was an F. None of the above were true. These ones easier to answer once you've kind of broken down the P part. So I've got normal force, I've got weight, I've got the force of friction, and I've got this P. This side right here I would call the adjacent side, the one right next to the theta. The adjacent side is going to go with cosine, so that's going to be P cosine of the angle. This right here is your opposite side, that's going to be sine, P sine of the angle. So I know that these are at a constant speed. That doesn't tell me P equals F, that tells me P cosine equals F, right? So if P cosine equals F, that means only part of E balances out with F, which means E must be bigger if only part of it balances out F. So that means P would be greater than F. So that's the first two. And now we need to talk about N and W. If you look at this right here, we're saying N plus P sine equals W. So if I need something N plus something to get to the weight, that means that N must be less than the weight. Or you can think about it as weight is greater because it's N plus something else. So N is less than the weight, so that is A. Here we've got a frictionless surface. If this angle is decreased, so if I pull now something like this, actually I'm going to break it down real quick. So actually this is the exact same as this, just take out the friction. If I decrease the angle, that means this force right here is going to decrease, which means the normal force would have to increase to balance out, because it still needs to hold up the weight, right? So you are holding up some of the weight, and now you lower the angle, you're holding up less of it, which means the surface has to hold up more of it so that it doesn't fall down. So this one would be increase. What happens to the acceleration of the block? So the acceleration is going to increase because now you're pulling it more to the side. So your force, right, is going to be, your net force in the direction you're trying to accelerate is going to be greater. Your P cosine is going to be greater. So this would increase as well. Free body diagrams, we've got mg, we've got normal, we've got friction force, and then this right here is pointing both down and to the right. So T some angle, T some angle. The side that is to the right, that's the adjacent side, so that's going to be cosine right here. The up and down is the opposite, so that's going to go to sine, that's the down part. And we're trying to find force of friction. I noticed that all my answers have mu, so that tells me it's probably going to be the mu Fn method of finding friction. So then you'll notice that Fn is equal to mg plus T sine. So because Fn equals mg sine, mg plus T sine of the angle, you're just going to substitute that in for mu, or not for mu, for Fn. So this is mu mg plus T sine, and that answer is A. 1, 2 is the force of 1 on 2, 2, 1 is the force that was supposed to be 2 on 1, it's just a typo. And W1 is the weight of box 1, and I'm ranking these three forces. So I actually made it super easy on you because the force of 1 on 2 and the force of 2 on 1, these have to be the same force. It doesn't matter which way it's accelerating. By Newton's third law, A on B and B on A, that's the same force. So I'm going to go ahead and just start with F12 equals F21 on all of these, because no matter what's happening, that is the same force. Now I need to relate W1 to what's happening. So I'm going to draw a free body diagram for box 1 because that's what I have the weight for. So 1 has weight 1 this way, and it's got the box 2 pushing it up, so F21. Now which one is bigger, whether W1 or F21 is bigger, just depends on which way it's accelerating. So if I'm moving up, that means your velocity is pointing up, and getting slower means your acceleration is against that in the opposite direction, so that's accelerating down. If we're looking at accelerating down, that means your down force is bigger, so W1 is greater than these two, which are equal to each other. Now, if your elevator is moving down and getting slower, moving down is velocity down, getting slower still means opposite direction to your acceleration, so that is pointing up. If your acceleration is up, F21 is greater, which means these two are greater and F1 is less. F1, W1. Here's moving up. and getting faster is in the same direction, so that's accelerating up. We already know what's happening for accelerating up. It's that FW is less than, these two are greater. And moving down and getting faster is acceleration in the same direction. Acceleration down means that weight 1 would be greater. So these would be your rankings for all 4 cases. Notice that if it's accelerating up, then the forces are like that. If it is accelerating down, the forces look like this. Block of mass M on a ramp. We want to give an expression for the force needed to move it up at a constant speed. So this F is my unknown. So I'm going to break down my forces. I've got F this way. I've got normal force this way. Because it is moving upwards, that means my friction is going against my motion, so friction force down. And then of course you've got FG pointing straight down. We need to break that up into the forces that are like across the normal and down the ramp. The part that is across the normal is mg cosine, and across the one that's down the ramp is mg sine. I would not try and do like draw your triangle to do those because your theta is actually down here. It gets very confusing. So just memorize for an inclined plane, breaking down the weight, the mg, it's mg cosine across the normal and mg sine down the ramp. And now it's at constant speed, which means these forces are equal, so Fn is equal to mg cosine. And F is equal to both of these, the force of friction plus mg sine. And then now I just need to replace force of friction with mu Fn. Mu Fn we just said was mg cosine plus this term, which was mg sine. So that's the friction force needed, not the friction force, the applied force. Here, again, we are moving up. So the friction force, I'm going to draw it on here. I actually don't need to find what the friction force is. It's telling me, call it F. So that's like a given. And then, of course, we have the mg cosine across from the normal like this. And then we've got the mg sine down the ramp. Now all we need to do is break down this force to up the ramp and like out of the ramp like this. So the up the ramp is going to be F cosine of phi. And then this force right here, the opposite side, the up or out of the ramp, I guess, would be your F sine. So you got Fn, F sine, little f for friction, mg sine, mg cosine, and then F cosine up the ramp. I want to find the acceleration of the block. So I know that it's moving upwards. The acceleration, I'm going to assume, is this way. So my net force is just F cosine phi minus both of these. So minus the friction force and minus mg sine. And then that's what F net is. I'm going to replace F net with ma. So to get a by itself, I just divide by m. So that's my acceleration. Now I would not cross off these m's because I only have an m in this term. I don't have them in all the terms. So just leave it like this. Find the coefficient between the block and the plane. So here, coefficient of friction, I'm of course using force of friction equals mu of n. Force of friction is just little f. Now I just need to find my normal force. So I know F sine phi plus Fn equals, right, we're looking at this direction, sorry, this is super messy, equals mg cosine. So Fn is just going to be mg cosine minus the F sine. And to get mu by itself, I just divide it all over, so F over all of it equals mu. Right here, we've got something going around in a circle. As soon as you see it rotating or in a circle, that's telling me centripetal force. So I've got the guys with weight, mg, pointing straight down. The reason he doesn't slide down isn't because there's a surface holding him up, right? The surface is actually this way. I can't hold him up. It's the friction force that's keeping him from sliding. The surface is actually pushing him to the center. So that's your normal. I know these two are balanced out because he doesn't fall down. So ff equals mg. And your Fn is acting as your centripetal force. Ff is mu Fn. Mg is mg. Fn you can't really put place, but I can replace Fc with mv squared over r. Remember your centripetal acceleration is v squared over r. That's on your equation sheet. So if you have acceleration and you want force, right, Fc is just mass times ac. So I just do mass here. So the net force is just mv squared over r. Alright, now that I have Fn as that, I can substitute in. So I've got mu mv squared over r equals mg. Divide by m, that crosses off. Trying to get v squared by itself, so I'm going to multiply this r up. I'm going to divide the mu over, oh wait, yeah, I'm looking for v. Divide the mu over, and then take the square root. So the square root of gr over mu. Planet X has twice the Earth's mass, 3 times the radius. What's the gravitational field? So gravitational field is talking about little g. Little g is gm over r squared. So if I have twice the mass and I've got 3 times the radius, that's going to be times 2/9. Now it's 2/9 smaller than Earth's gravitational field. Earth's gravitational field is 10. So 2/9 of 10 gives me around 2. The magnitude of the gravitational field on the surface of a particular planet is 2g. If half the mass, what is the planet's radius? So again, we're doing the gm over r squared is your g. Now I have g, half the mass. I'm looking for what I do to r squared in order to end up with times 2. So think about it. If I have 1/2 right here, I know I'm dividing by a fraction in order to get bigger. You need to multiply by 4, which means you need to divide by 1/4. Because when you divide by 1/4, that's the same as multiplying by 4 over 1, which would give me 2. So to have 1/4 on bottom, you need to have a 1/2 right here. So you need half the radius, that's just r over 2. R over 2 is the same thing as half the radius. Right, orbital velocities. V is square root of gm over r. That is for something orbiting, like in outer space, a planet. And it's the mass of the center object that matters. Mass of the satellite does not. 2 objects orbit the same sun. The second object at a radius of 4r, what's the velocity? So square root of gm over r, but now I'm plugging in 4r. So this is a factor of root 1/4, right? 1 on top, 4 on bottom. So that's going to be times 1/2. Half the velocity is v over 2. I have now 1/16 the radius. Still talking about velocities and using my v equation. Now when you have 1 over 1/16, that just becomes times root 16, which is times 4. So it'd be 4 times the velocity c. Right here, they both start from rest, they both end at the same height of 0, so their change in energy should be the exact same for potential, because I start with MGH and with 0 potential. Now your kinetic energy, they both start with 0, kinetic is 0, because they start from rest. Now, if they both end with a kinetic energy K, they actually don't end with the same kinetic energy K because it says that there is friction. These two do not have the same work done by friction because this one is a greater distance traveled. So because it has a greater distance traveled with a greater friction force, it's going to have more work done, which means it has less energy, right? So this is less kinetic. This is more kinetic energy because it's not losing as much of its energy. So the one that has the greater kinetic change in kinetic is ramp 1 because it went from 0 to more kinetic compared to 0 to less kinetic. So ramp 1 has a greater change in K. And the one that reaches the bottom first is 1 because it's steeper, it'll have a greater acceleration. Doesn't necessarily mean that steeper has a greater velocity, right? You can, if this were frictionless, they would come down with the same velocity. This one would just do it in a quicker amount of time. Same velocity at the end though. We are looking for the maximum height, so we're going from all kinetic energy to all potential because at the max height it stops moving, right? It turns around. So that's 1/2 mv squared goes to mgh. The length of the vine is not how high he goes, right? This is the length of the vine. It's not, it's totally irrelevant. Mass cancels, so that tells me mass is irrelevant. Multiply by 2 and take the square root. So the only thing, oh wait, no, we're trying to get h, sorry. So this is v squared, 1/2 v squared divided by g is your height. Also v squared over 2g, it's the same thing. So the only thing that your maximum height depends on is the acceleration due to gravity and how fast you were at the bottom. Here we've done this question a lot, but we're talking about total mechanical energy. And we know friction and air resistance are negligible, which means that energy is going to be conserved. So if energy is going to be conserved, your total energy should remain the same the whole time. Your kinetic energy is increasing and then decreasing. Your potential energy is decreasing and then increasing, but the total amount, the potential plus the kinetic at each point, should be the same the whole time. Here we've got 10 centimeters and 5 centimeters. This is uncompressed, which means you have no spring energy. If I stretch it now to 15, I have an x of 5 centimeters. That means your x is 0.05 meters, because centimeters divide by 100 to get to meters. And now I hold some spring energy. I'm going to actually calculate 1/2 kx squared. K is your spring constant, which is 200. X is 0.05. Square that, and you get 0.25. So this now has a spring energy of 0.25. So my change in spring energy was from none to 0.25 joules, and I gained 0.25 joules. Now, that was not the only energy changing. You should have noticed that your height changed as well, which means your gravitational potential energy changed, which is mgh. Now, I don't know the actual height above the ground, but I do know that it changed by this amount, so I'm just looking for the change anyway. So it's the change in height. Mass is 1, g is 10, change in height was 0.05 meters, and that's 0.5 joules. But I lost that height, which means I lost that potential energy. So if I gain 0.25 and I lose 0.5, that means I've lost overall, so plus 0.25 minus 0.5 equals minus 0.25, so then I decrease by 0.25, which is B. Alright, we have force and distance graph. I want to know which one will be moving the fastest at the end. So as soon as you see force and distance, newtons and meters, you should for sure be doing area under the curve. This area is going to represent the work. That work represents the change in energy. So the one that has the greatest change in kinetic is the one that will be moving the fastest. So the one that has the greatest work was force 2 because it has a greater area. That means it will gain more kinetic energy, which means it would be moving faster. Alright, Slim Jim runs at full speed, 5 meters per second, and grabs the rope and swings up. How fast will he be moving when he is 0.9 meters high? So here it's definitely all kinetic. Here I'm going to assume it's some kinetic and some potential because I'm asking for how fast he's moving. It didn't say this is at like the maximum height. So I've got 1/2 mv squared equals mgh plus 1/2 mv squared. I'm looking for this missing velocity. You'll notice that the masses cancel out. So I do have 60 kilograms, but it doesn't really matter. 1/2, the initial velocity was 5, equals g. The height I'm asking for is at 0.9 plus 1/2 v squared. So this is just 9. Half of 25 is 12.5. Subtract that over, you get 3.5. Multiply by 2, you get 7. So then your velocity is the square root of 7, which is also like 2 point something? 2.67 or 2.65. Same thing. Here, air resistance and friction are negligible, which means that energy is conserved. That doesn't look like words. So as I go from A to B, as you're going up, your potential should be your potential should be increasing, you're going higher. Your kinetic energy should be decreasing, you're getting slower as you move up. And your total energy should be staying the same. So C, KE decreases and total remains the same. A person lifts a box from the ground to a table 0.6 meters high at a constant speed. How does the total mechanical energy of the Earth box system change? So if you have on the table and then I move it up at a constant speed means you're keeping the same kinetic energy. But see how your potential energy just increased? If one energy stays the same and the other one increased, that means overall your total energy increased. So we're between B and D. Now we would have energy increasing if there was positive work done, energy putting into the system, so B makes sense. Negative work would be taking energy away. Make sure you also do the whiteboard practice. I'll be uploading that PowerPoint and the answer key to be fully prepared.